Welcome, everyone. For today's prep, we're going to see how to find the area for a region that looks like this. So we have a section that goes below the x-axis, and we have a section that's above the x-axis. And we want to find just the total area for those shaded regions. So our strategy for doing this, we can't just integrate the function between the two endpoints there, because the integration kind of smooths it out. It tries to cancel off the stuff that's below with the stuff that's above. So the idea, our strategy, is we're going to break apart the integration. So we're going to first do an integral to get the area for the region that's below, and then we'll do a separate integral to figure out the area for the region that's above, and then once we have those two separate areas, we can add the results. And kind of the key thing here is we need to know, when does our function cross the x-axis? So we want to find the x values where our function intersects the x-axis. And so let's try out an example. Example 1, we're going to find the area of the region between the x-axis and the curve for the function x squared minus x, where we're going from x equals 0 to x equals 2. All right, so first step, we want to get the intersection points. So how do we do this? Well, we take our function and we set it equal to 0 and solve for x. So we're going to set f of x equal to 0 and then solve for x. So if we do that, we get the equation x squared minus x is equal to 0. So we're just taking our function. And, we can solve this any different way we want. In this case, factoring is going to be the way to go. So we could factor. So we get x times x minus 1 equal to 0. And then each of those factors is going to give us an intersection point. So at x equals 0 and at x equals 1. And we have the graph of this function right down here. So you can kind of see, yeah, that seems to agree. It crosses the x-axis at 0 and 1. But just to confirm this, we can look at the graph, but we don't know exactly if it's at that point. So doing the algebra here just confirms that, yeah, this is the exact place where it crosses. All right, so we're interested in figuring out the area for this shaded region. And like we mentioned, if we try to just integrate going from here all the way to here straight through, the integration tries to smooth it out. It's going to cancel off this section that's below with some of the part that's over here that's above. And we don't want to cancel. We just want to know how much area is over here and how much area is over here. So the idea is we're going to break up our integration. All right, and the way we're going to break up our integration is using these intersection points and our interval. So we want to do a sign chart, or we want to look at our interval a little bit more closely. And so let's draw it. We know we're going from 0 to 2. So let's just draw our x-axis, or just the section there. And then we plot any of the intersection points that we found. So 0 is already kind of an endpoint. And the only other intersection point that's inside this interval is, well, it's actually right in the middle. It's x equals 1. So what that intersection point does is it's splitting up our x-axis into kind of two different sections. So we have the section going from 0 to 1, and then we have the section going from 1 to 2. And if we didn't have the graph of the function just sitting right here, we're going to want to figure out which of these intervals is our function above the x-axis and which of them is it below. So looking at the graph, we can see that in between 0 and 1, the graph of the function is below the x-axis. So on this interval, it's below. And then in between 1 and 2, that's where the function is above. Now, if you didn't have the graph, you could figure this out by just doing a sign chart. So you could pick a test number. So for the first interval, maybe like 1/2. Plug it into the function and just see, do you get a positive value or a negative value? And actually, you can even use the factored version. So if we were to plug 1/2 in, we'd get 1/2 times 1/2 minus 1. That 1/2 minus 1 is going to be negative. So you would see that f is negative on that first interval, which means it's below. And then same idea, we could pick a test number for the next interval. So maybe like 3/2, and we could plug it into the factored version. And 3/2 is positive, and then 3/2 minus 1 also positive. So the fact that you'd be getting a positive value there tells us that the function is above the x-axis. All right, so once we figure this out, now we're ready to set up our integrals, and we're going to do 2 of them. So we're going to figure out the integral from 0 to 1 of our function. And then separately, we're going to integrate from 1 to 2. So we got to break this up. And what we're going to see is that when we calculate this integral going from 0 to 1, because our function value is negative, this integral is going to be negative. And when we do the integral from 1 to 2, because our function values are all positive there, this integral is going to be a positive value. So we're going to have to make some slight adjustments after we calculate these integrals. So now we're integrating. All right, so let's start. Let's get the antiderivative. So the antiderivative of x squared, if we do our power rule, is 1/3 times x cubed. The antiderivative of minus x is minus 1/2 x squared. And the nice thing is we're integrating the same function. So we can reuse our antiderivative. The antiderivative is not going to change here. All right, so for the first one, we're going to then evaluate going from x equals 0 to x equals 1. And then for the second one, this is where we're evaluating from x equals 1 to x equals 2. All right, so let's see what we get. So for the first one, top number gets plugged in first when we do the evaluation. So when we plug 1 in, we're going to get 1/3 minus 1/2. And then we subtract, and then we plug 0 in. So when we plug 0 in, powers of 0 are just 0. So we end up with nothing there. So again, top number gets plugged in first. That's what we're seeing here. And then bottom number gets plugged in second. That's what we're seeing here. And doesn't matter in this case, but we do subtract those 2 values. All right, so now let's evaluate for the second one. So it's the same antiderivative, but now we're plugging different numbers in. So top number gets plugged in first. So when we plug 2 in, we're going to get 8/3 minus 2. And then when we plug 1 in, we're going to get 1/3 minus 1/2. So we actually know what we get there. All right, so the top number went in first, the bottom number went in second, and here it actually does matter. We are subtracting these values. Okay, so let's simplify these 2 expressions. So for the first one, if we get a common denominator, 1/3 minus 1/2 is negative 1/6. So just like I promised, for this first integral where we're going from 0 to 1, because our section there, our region is below the x-axis, if we integrate going from 0 to 1 without making any adjustments, we end up with a negative value. Okay. Now if we simplify this, this should be a positive value because our function is above the x-axis on this interval. So, and when you do this, Let's simplify. So 8 over 3 minus 2, we could get a common denominator there. So this is the same thing as 6 over 3. So this first part is just 2 over 3 when we simplify. And we know that this is negative 1 over 6, so we have minus negative 1 over 6. And the double negative becomes positive. And again, if we get another common denominator, we can add these together, and we end up with positive 5 over 6. All right, so how do we get the area from all this? Well, now we're ready for our area. So the area of the region is going to be the area that sits above the x-axis plus the area that sits below. So we kind of broke this apart. So for the area above, this is the region that sits above. And this is the region that sits below. So the area for that region above, that's what this 5 over 6 represents. We don't have to make any adjustments. So this area that sits above is 5 over 6. And that's because we integrated from 1 to 2. So we're able to fill that in. The area above is 5 over 6, no adjustment. Now we're going to add to that. And now to get the area that sits below the function, or that sits below the x-axis, that region is the integral from 0 to 1. That integral value is negative 1 over 6. The negative is just telling us that the region's below the x-axis. So we don't really want to know that. We want to know what's just the size of that region. What's the area? And so that's what the 1 over 6 represents. So the area below is just 1 over 6. So we had our area above was 5 over 6. The area below was 1 over 6. And so just a key thing here is that the integral going from 0 to 1 of our function, we had to kind of get rid of that negative. So we saw that it was negative. And the interpretation is that the negative is just telling us here that it's below the x-axis, and the actual number part is the area that sits below. So when we found this integral, we had the negative in front. That's just telling us we're dealing with a region that's below. And the 1 over 6, that's actually the size of the region. So if we add these two values together, then we get that our area, the total area, is 1. Okay. So we're going to practice a few more area type calculations like this in class. So we'll see you then. Bye-bye.